Let's discuss Raoulat's law case 2 in this video. In the previous video, we discussed Henry's law, which is for gaseous solute in liquid solvent. Here we have taken a non-volatile solid solute in a volatile solvent, that is in a liquid solvent. A binary solution is formed by dissolving a non-volatile solid solute in pure solvent, that is in a liquid solvent, that is volatile in nature. So example for that case is sodium chloride in water. So we take this solution and find out how the vapor pressure changes when a non-volatile solute is added, non-volatile solid solute is added to a liquid solvent. That's we are going to discuss. Then we have to derive the Raoulat's law case 2 expression. So you take a closed container where you have a pure solvent. Now the vapor pressure of the pure solvent is taken as P0 of the solvent. Now you add a non-volatile solute into the solvent to form a solution. Now find out what is the vapor pressure of the solution, that is taken as P solution. So when you compare the vapor pressure of the solution and the vapor pressure of the pure solvent, the vapor pressure of the solution is found to be lower than the vapor pressure of the pure solvent. This is because when you take a pure solvent, the surface of the solvent is occupied only by the solvent molecules. So therefore more and more number of solvent molecules will go to the vapor state and the vapor pressure is found out. But here when you take a solution, the surface will be occupied by both solvent as well as the solute. Red you take it as a solute and black you take it as a solvent. So both solute as well as the solvent will be present on the surface. Now the solute is non-volatile, so they will not escape to the vapor state, but solvent being volatile in nature, they will go to the vapor state. Therefore what will happen, the number of solvent particles occupying the surface will become less, therefore the number of solvent particles going to the vapor state also decreases, therefore the vapor pressure decreases. So when you add a non-volatile solute into solvent, there is a lowering of vapor pressure. So P0 solvent is greater but P solution is decreased, therefore there will be a lowering of vapor pressure when you add a non-volatile solute into pure solvent to form a solution. So now you find out the vapor pressure of the solution. The vapor pressure of the solution is mainly due to the number of solvent particles present here. Therefore we can say that the vapor pressure of the solution is directly proportional to the mole fraction of the solvent molecules. So P solution is directly proportional to XA. Remove the proportionality, introduce a constant K. So P solution is equal to K into XA. But we know that the sum of mole fraction of the solute and solvent will be equal to 1. So XA plus XB is equal to 1. But when you take a pure solvent, we don't have solute here. Therefore XB can be taken as 0. So when you substitute XB is equal to 0, then XA will be equal to 1. Now you substitute this XA is equal to 1 in this equation. P solution is equal to K into XA. So you will be getting P solution is equal to K. Since here the vapor pressure is due to only the pure solvent, the P solution, that is vapor pressure of the solution, can be replaced by vapor pressure of the pure solvent, because we are considering XB is equal to 0. So therefore the vapor pressure is due to only the solvent molecules. So solvent alone we have considered. So we are replacing P solution as P0 of solvent. Now you substitute K is equal to P0 of solvent in this equation. So you will be getting P solution is equal to P0 solvent into XA. So now you bring P0 solvent to this side. So P solution divided by P0 solvent is equal to XA. So you write here, rearrange like this. 1 minus P solution divided by P0 of solvent is equal to 1 minus XA. Both the side you write it as 1 minus 1 minus. So you will be getting this expression. Now you take LCM. So P0 of solvent minus P solution divided by P0 of solvent is equal to 1 minus XA. But 1 minus XA is equal to XB, because XA plus XB is equal to 1. Therefore 1 minus XA will be equal to XB. Therefore you can write it as XB here. So that is nothing but the mole fraction of the solute. So P0 of solvent minus P of solution divided by P0 of solvent is equal to the relative lowering of vapor pressure, because P0 of solvent minus P solution is lowering of vapor pressure. This lowering of vapor pressure we are relating to the vapor pressure of the pure solvent. Therefore it is called as relative lowering of of vapor pressure. We are relating the lowering of vapor pressure to the vapor pressure of the pure solvent. So it is called as relative lowering of vapor pressure. And this relative lowering of vapor pressure is equal to the mole fraction of the solute alone. Because of the presence of the solute, there is a lowering of vapor pressure. Therefore, the relative lowering of vapor pressure will be equal to the mole fraction of the solute. So the Raoulat's law, this is what we call it as Raoulat's law. So Raoulat's law can be stated as the relative lowering of vapor pressure of an ideal solution containing a non-volatile solid solute is equal to the mole fraction of the solute at a given temperature. So this is the Raoulat's law case 2. So what do you mean by ideal solution? So ideal solution should satisfy following. The first one, the solution which obeys Raoulat's law over the entire range of concentration can be taken as an ideal solution. That means Raoulat's law means PA is equal to P naught AXA, PB is equal to P naught BXB, and P total. So both two expressions are there for total pressure. Both the expressions should be satisfied by the solution, and also the graph also should be satisfied by the solution. Then the solution is taken as an ideal solution. The next condition is the intramolecular attractive forces between A and A, B and B, and A and B should be the same. That is, similar intermolecular attractive forces should be there between solute, solvent, and solute, solvent. So when you take an example, here we have taken and two solute molecules, there will be an intermolecular attractive forces. And here the solvent is taken, there will be an intermolecular attractive forces. When solute and solvent is added, there will be a solute and solvent. Between them, there is an intermolecular forces. This intermolecular forces should be the same as these two. Then the solution is taken as an ideal solution. The next, that delta V mixing should be equal to 0. That is, the change in volume on mixing will be equal to 0. You take a solute 5 ml. Solvent, you take a 5 ml. You add solute and solvent into another beaker so that form a solution. So the total volume will be equal to 10 ml because we are adding 5 ml of solute, 5 ml of solvent. So total 10 ml. So you find out what is change in volume. Change in volume is equal to V solution minus V of solute plus V of solvent. That will be equal to 0. So 10 minus 10, that will be equal to 0. If delta V mixing is equal to 0, then the solution is taken as an ideal solution. Then delta H mixing should be equal to 0. That is, the enthalpy change on mixing should be equal to 0. You take an example. You take a solute AA plus BB. They will combine to form AB. How many AB are formed? 2 AB will be formed. So the energy required to break A and A. So there should be a breaking of A and A. So to break A and B, energy should be supplied. So 20 energy is supplied. For example, you take. To break BB, 20 energy is supplied. But to form AB, energy should be liberated. Because during the bond formation, energy is liberated. During the breaking of bond, energy should be supplied to break the bond. But formation of the bond, energy is liberated. So to form 1 AB, 20 energy is liberated. To form 2 AB, so 2 into 20, that is 40 energy is liberated. So when you find out the change in enthalpy, 40 minus 20 plus 20, 40 is equal to 0. So delta H, that is enthalpy change on mixing, should be equal to 0. Then the solution is taken as an ideal solution. Then fifth condition, the pressure calculated, total pressure calculated by Raoulat's law, theoretical calculation. That is by using a formula derived from Raoulat's law. That should be equal to the pressure which is experimentally observed by using manometer. Then that is delta P should be equal to 0. Then it is considered as an ideal solution. So to have an ideal solution, the solution should obey Raoulat's law. The intermolecular attractive forces should be similar between solute and solute, solvent, solute and solvent. Then delta V, that is change in volume on mixing, should be equal to 0. Enthalpy change on mixing should be equal to 0. Change in pressure should be equal to 0. So two problems. That is, before that we will go for some example. Example for ideal solution: benzene and toluene. You can take N-hexane and heptane, ethyl bromide and ethyl iodine, chlorobenzene and bromobenzene can be taken as an ideal solution. So in your book, a book chapter. At the end of the chapter there is evaluation given. So here I have taken 8th question as well as the 13th question from the evaluation side. So you take the 8th one. P1 and P2 are the vapor pressures of your liquid components 1 and 2 respectively of an ideal binary solution. If X1 represents the mole fraction of the component 1, then the total pressure of the solution formed by 1 and 2 will be. So here you can take two components are taken 1 and 2. Vapor pressures are P1 and P2. So you can write the total pressure is equal to P1 X1 for the component 1 plus P2 X2 for the component 2. Now you substitute X1 is equal to 1 minus X2 in this expression because total mole fraction of the component will be equal to 1. So P1 into 1 minus X2 plus P2 into X2. Simplify this one. So P1 minus P1 X2 plus P2 X2. So you can write P1 minus you take X2 outside minus X2 you take outside. So minus X2 is equal to P1 minus P2. So this is like the third expression, that is C option. So C is the correct answer. According to Raoulat's law, the relative lowering of vapor pressure of a solution is equal to the mole fraction of the solute. We already discussed. So here we have discussed. So the relative lowering of vapor pressure is equal to the mole fraction of the solute. Therefore, B is the correct answer, mole fraction of the solute. Thank you for watching this video. Next video we will discuss non-ideal solution.